Well, good morning. It's Christmas Eve here in Seattle, and it's just below freezing, so maybe we might get a little bit of snow this evening, white Christmas tomorrow. Anyway, I wanted to do a quick video to submit to Dave Jones' EEVblog, hopefully for inclusion in his holiday videos. Now, the video in question that I'm doing here is responding to a viewer's question on my channel, where they looked at a power meter I had and wanted to know, with that power meter, how they would go about working out the sensitivity of a crystal detector. So here is a set of crystal detectors that I have. This one is an 8470B, and it's an N-type connector, and it goes from 10 megahertz to 18 gigahertz. The 8472B is here in the middle, and it's an SMA type connector, and it goes from 10 megahertz to 18 gigahertz as well. And then on the right here is an 8473C, and it is a 3.5 millimeter connector, which is physically the same as an SMA, but they're actually different because of the tolerances. So if you're ever using these things, mostly you will have SMA cables. So it's a good idea to have a little saver in the connector there, so that you wear out this saver and you can throw that away and replace it. Anyway, this is a 10 megahertz to 26.5 gig crystal detector. Now, what these crystal detectors do is they make use of the square law area of these Schottky diodes. And what that means is that below a certain power, when you put the power into a crystal detector, the slope of a line that shows the action or shows the correlation between power and the output voltage becomes proportional and linear. And the viewer, let me move these out of the road here and we'll zoom out a little bit. The viewer wanted to know how to work out, let me move that, how to work out what K is here. And K is the sensitivity of the detector. And so if we look over here, you can see how the power input relates to the detector law. And what we're trying to do is get a linear region here, and you can see this linear region part here. And so they call this, based off this equation here, they call it the square law region because alpha here becomes 2 and hence squared. So when you work out what the equation is, it's the voltage out of the crystal detector is the sensitivity K square root of the power squared, which is just the power. So you become linearly related to the power. And you can see the voltage. You can see that the lines up here are very linear based on the power and the frequency, 2 gigahertz here for the voltage that's being detected. And so he wanted to know how to specifically get that calculated voltage for K. Now, if we jump out here and take a look at the specs, you'll see that typically the sensitivities, let me move that down. Typically the sensitivities are quoted in millivolts per microwatt. And so the K value as a unit of measure, as far as I'm aware, is not well used. So anyway, on most of the data sheets, you'll see sensitivity as millivolts per microwatt in that square law region. And what we want to do is to take these detectors and go ahead and calculate their sensitivity. So to do that, I'm going to need to use three pieces of gear actually. So let's zoom out a bit so you can see these things in a row. The 3 pieces of gear are going to be a signal generator that's capable of delivering minus 20 dBm and we'll pick a middle frequency of 10 gigahertz. I'm going to use a power meter that enables me to check the power at the measuring point, and this will be the measuring point here where I have my cable connected to the N-type connector here, and I want to set this to be minus 20 dBm. And then we'll use a digital multimeter where we can connect it to the B and C connector here on the end, which will show us the voltage that will occur. So let's go set this up. The first thing that we're going to go do is set up the signal generator. Okay, So the signal generator I'm using is my 8673B, and I primarily use this as a local oscillator for a microwave converter. But I'm going to use this this particular case because this has a vernier control on the output, and it enables me to, very finely adjust the power. I thought about using my 8340B, which I have here, but unfortunately at minus 20 dBm is an attenuator step, so it's very difficult to get the accuracy between to get minus 20 dBm. So let's go in and we'll select the range of minus 10 here. And if you see the vernier, let me put the output on. And now you see the vernier here. You can see in the little dial that as I move that back and forwards, we're going between minus 10 from that range, so it's minus 20 dBm, up to 3 dBm. So minus 10 dBm would be there, and that lets me go and get the accuracy at that point. I could also go down a range and then just sit here and play around here. Now I want to set my output to be 10 gigahertz. We have our 10 gigahertz there. We have our automatic level control as being internal. So that's a good enough start for us to go and start measuring the power that we're going to deliver out of that N-type connector. The next thing we need to do is set up our power meter. So here is our power meter. So the first thing we'll do is we'll do a pre-select. So we'll make sure that it's all set up. We're going to go in and configure it. So these power meters, in this particular case, it's an E4418B. You can use the 8400 series power sensor. And this is an 8481A power sensor that goes from 100 megahertz to, or goes actually from like 10 megahertz up to 18 gigahertz. And you can see that I have the power factors here. Now this has been off to Keysight and has been calibrated, so it should be reasonably accurate, given that these things are an open loop power meter. So unlike the 432s or the crystal detectors, which give you an absolute value of the power they're actually measuring, these work on the accuracy of the underlying power reference here. So this is a 50 megahertz, 0 dBm power meter, 1 milliwatt power meter reference. So we're going to put this on here, and then we're going to zero that so that this thing knows what 0 dBm is. So we'll just screw this on here. Now, I'm going to go in and select a table, and we're going to go and make sure that you can see here that I have my 8481A table. So that's taken all those calibration figures off the side of the unit. I've entered those in. So now that we've got that set, I can come over here and go to 0, and we're just zeroing out the thermocouples. We've got one that will measure the ambient temperature. We've got one that will measure the RF that's coming in. And so now we can just go in and calibrate that. And you can see that the power reference turns on here. And there we go, we're calibrated. So now the next thing I need to do is actually put a frequency in. And I know that we're going to be working at 10 gigahertz. So let's go in and set that down to 10 gigahertz. And here you'll see now the calibration factor is set for 94.5%. And this is how the unit knows what the losses are going to be in the detector. So now that we're set up there, what I need to do is just go and hook this up to the to our cable, and we'll now measure and get our minus 20 dBm. So you can see now that I'm measuring minus 12. So I'm just going to grab that vernier and start taking that down until we get to about minus 20. And we're going to try and get as close as we can. There we go, that's nice. And it'll bounce around a little bit there, but you know, a couple of hundredths of a dBm, I'll take that. All right, so now we just need to go back to our crystal detectors and we can start doing our first measurement. Okay, so we have minus 20 dBm coming out of here. So the next thing for me to do is to hook this up to the crystal detector and to the DMM. And that's a Rigol DM 3058. So let's just hook this up. And now we're going to be reading a voltage here somewhere in the millivolts. So what I have is I have a little app here that I wrote to pull the data off the Rigol because it's in a sort of an inconvenient place. And so here we have 6.69 millivolts, 6.7 millivolts. So let's just say that that's going to be our value. Now, if you remember, the sensitivity was going to be, or the voltage spec was in millivolts per microwatts. And so it's going to be 6.7 millivolts divided by 10 microwatts. So, because we're at minus 20 dBm. So we're going to get 0.67. And if we come back here and zoom in, here you'll see that for sensitivity, it's greater than 0.5 millivolts per microwatt. So, you know, we're greater than that at 0.67. So we're in spec, and that's given us the sensitivity. Now, if we want that K factor, we should go in and bring all of those up to volts and watts. So that's 1,000 and a million. So basically, we're just going to multiply this number when you do the math by 1,000. So let's go and see, and it's about 670. So to work out from this formula here, using the crystal detectors in that sensitivity region, to get K was fairly straightforward. And for this particular sensor that I have here, it's about 670. Now, these are not metrology grade connectors. There's some loss in the cables, all that sort of thing. But that takes you through the process of how to go and get that. So I could go and do it again using each of these, or I could go and try a different frequency. Remember, this sensitivity will change based on the frequency, not by a lot, but it will change. So if you're going and needing this value for 18 gig, you need to do it at 18 gig, measure it, and then you can work back. Anyway, I hope you found this interesting, and I hope this video makes it onto the EEVblog channel. If it doesn't, it'll still make it onto my site, as Dave said. Anyway, check below. My channel is TGSoapbox, and come on over. I have a bunch of videos about old Hewlett-Packard test gear, and or old test gear, and how you can use it and how to repair it. Anyway, look forward to seeing you in the comments. Catch you later. Bye.